All tech companies, including Google, Facebook, and Amazon, need to count unique visitors to their websites and track many other variables. Billions of entries streaming in every second from around the globe. Traditional counting methods would require storage so vast it would challenge the limits of even these tech giants' immense resources. What's surprising is that these companies, with all their computational might, don't actually know exactly how many unique users visit their sites. Instead, they deliberately use algorithms that provide just an estimate, a calculated approximation that's precise enough while using a fraction of the resources a perfect count would require. This is the world of probabilistic algorithms, mathematical approaches that trade absolute certainty for remarkable efficiency. And among these clever mathematical shortcuts, HyperLogLog stands as perhaps the most elegant solution to an otherwise impossible problem. Imagine you're handed three colored cubes, red, green, and blue. How many unique colors do you see? Three, obviously. Anyone can count that. But what if I gave you 1,000,000 cubes with potentially thousands of different colors? Suddenly, the task becomes monumentally difficult. Now scale this up to the digital realm. Every day, tech companies need to answer questions like, how many unique users visited our website today? How many different search terms were entered in the last hour? How many distinct products did customers view? How many unique IP addresses connected to our servers? These questions fall under what computer scientists call the distinct count, or cardinality problem, determining how many unique elements exist in a dataset. And at internet scale, this seemingly simple counting task becomes one of computing's most resource-intensive challenges. The obvious solution appears straightforward. Keep a list of everything you've seen before. Each time you encounter an item, check your list to see if it's new. In programming terms, this is like using a set data structure or a hash table to track unique elements. For small data sets, this works perfectly. But for companies like Google or Facebook, this approach quickly breaks down. For internet-scale applications, traditional exact counting methods would require hundreds of terabytes of memory. Before diving into probabilistic solutions, let's understand why exact counting becomes so problematic at scale. There are essentially two traditional approaches. 1. The naive method. Keep a list of everything you've seen so far. When a new item arrives, check your list to see if it's a duplicate. This approach is like maintaining a simple table where each row represents an item you've encountered. Every time you see something new, you add a row to your table. The problem is that this table grows endlessly. If you're tracking millions of unique items, like website visitors or product IDs, your table becomes enormous. This approach requires a lot of memory. The storage grows linearly with the number of unique items, meaning if you have 10 million unique users, you need enough memory to store 10 million records. 2. Hash-based approach. Store items in a hash table or set for faster lookups. This is similar to organizing your data into a special kind of table with an index, like how a library catalog helps you find books quickly without checking every shelf. While lookups are faster because you can jump directly to where an item should be rather than scanning the entire list, the memory requirement still remains proportional to the number of unique items. It's like having a more efficient filing system, but you still need one folder for each unique item you're tracking. Both these methods suffer from the same fundamental limitation. As the number of unique items grows, so does the memory requirement. And in the age of big data, this scaling problem becomes insurmountable. When processing petabytes of data, the memory requirements for exact counting become prohibitive, notes Piotr Indyk, professor of computer science at MIT and a pioneer in algorithmic techniques. You either need to distribute the computation across many machines, which introduces its own complexities, or find a way to approximate the answer. This is where probabilistic algorithms enter the picture. To understand HyperLogLog and similar probabilistic algorithms, we first need to appreciate a fascinating property of random events. Specifically, what happens when you flip a coin multiple times looking for streaks? Imagine flipping a coin and counting how many heads you get in a row before seeing tails. Getting one head in a row has a 1/2 probability, 50%. Getting two heads in a row has a 1/4 probability, 25%. Getting three heads in a row has a 1/8 probability, 12.5%. Getting five heads in a row has a 1/32nd probability, about 3%. Getting 10 heads in a row has a 1/1024th probability, less than 0.1%. 20 heads in a row has a probability of approximately 1 in a million. But here's the crucial insight. If you keep flipping long enough, eventually you'll see longer and longer streaks. And remarkably, the length of the longest streak you've observed tells you approximately how many flips you've made. If your longest streak is 5 heads in a row, you've probably flipped the coin dozens of times. If your longest streak is 10 heads in a row, you've probably flipped hundreds of times. If your longest streak is 20 heads in a row, you've probably flipped about 1,000,000 times. Mathematically, if the longest run you've observed is r, the estimated number of flips you've made is approximately 2 to the power of r. This isn't exact, there's variance involved, but it's a remarkably useful approximation. This relationship between the length of the longest streak and the number of attempts is the mathematical foundation of HyperLogLog. HyperLogLog was invented by Philippe Flageolet, a French computer scientist, and his collaborators in 2007 as a refinement of earlier log-log algorithms. The hyper prefix was added because it enhanced the statistical properties of the original approach. Here's how HyperLogLog works in practice. 1. Hashing. First, we transform each item we want to count, user IDs, search terms, etc., into a random-looking bit sequence using a hash function. A hash function is like our magic machine that converts objects into seemingly random numbers. Crucially, a good hash function always produces the same output for the same input. If user A123 visits, the hash might output 101101001 ... but it will always produce exactly that sequence for user A123. Bit pattern. Analysis. Instead of storing the entire hash value, which would be as bad as storing the original items, we look at the bit pattern in the hash. Specifically, we count the number of leading zeros in the binary representation of the hash value. A pattern starting with 0, 1, 1 leading 0, occurs with probability 1/4. A pattern starting with 0, 0, 1, 2 leading zeros, occurs with probability 1/8. A pattern starting with 20 leading zeros occurs with probability about 1 in 1,000,003. Maximum observation. We only remember the maximum number of leading zeros we've seen so far. This is our longest streak equivalent. Fourth estimation. The cardinality, number of unique items, is estimated as approximately 2 to the power of the maximum leading zeros observed. If our longest run of leading zeros is 20, we estimate we've seen around 2 to the power of 20, approximately 1,000,000 unique items. The brilliance of this approach is that we've reduced the problem of counting potentially billions of items to tracking just a single number, the maximum number of leading zeros observed. Instead of requiring memory proportional to the number of items, we now need just a few bytes, regardless of how many items we process. There's an obvious problem with the basic approach described above. What if, by sheer luck or bad luck, we see an unusually long or short run of zeros? Our estimate would be way off. For example, even with just 1,000 unique items, we might by chance see a hash with 15 leading zeros, suggesting about 32,000 items. Or perhaps never see more than 5 leading zeros, suggesting only 32 items. Both would be far from the true count of 1,000. Flageolet's solution was elegantly simple. Don't use just one counter, use many. HyperLogLog divides all possible inputs into buckets, typically 1,024 or 2,048 of them, and keeps a separate counter for each bucket. Here's how the bucketing works. 1. When an item is hashed, we use the first few bits of the hash to determine which bucket the item belongs to. For example, with 1,024 buckets, we'd use the first 10 bits to select a bucket. 2. For each bucket, we track the maximum number of leading zeros seen in the remaining bits of the hash. 3. When we want our final estimate, we combine the values from all buckets. Originally, this was done using a harmonic mean, though newer versions use other averaging techniques. This approach dramatically reduces the variance. If one bucket gets an unusually large value by chance, it has minimal effect on the overall estimate. With 1,024 buckets, HyperLogLog typically achieves an accuracy of about 2 to 3% from the true value. Remarkably, all this requires only a small, fixed amount of memory. If each bucket's counter can be stored in 5 bits, allowing counts up to 31 leading zeros, sufficient for most practical applications, then 1,024 buckets would require just 640 bytes, enough to estimate cardinalities into the trillions. Google's implementation of HyperLogLog, called HyperLogLog++, and published in 2013, includes several refinements to the original algorithm. 1. Bias. Correction. The original algorithm has systematic biases for certain cardinality ranges. Google implemented correction factors to address these biases. 2. Sparse representation. For small cardinalities, Google's implementation uses a more memory-efficient representation, switching to the standard approach only when necessary. 3. Precision control. Google's version allows adjusting the number of buckets based on the required precision, making it adaptable to different use cases. One of the most valuable features of HyperLogLog isn't just its efficiency, but its mergeability. If you have two HyperLogLog counters that have been tracking different streams of data, you can combine them to get an estimate as if you had processed all the data together. This property, known as set union capability, is crucial for distributed systems. Different servers can process different portions of the data, maintain their own HyperLogLog counters, and then merge these counters to get a global estimate, all without double counting duplicates. This mergeability comes for free due to how HyperLogLog works. The maximum leading zeros observed across all servers is simply the maximum of the maximums from each server. This allows companies like Google to distribute counting across thousands of servers and then aggregate the results efficiently. To truly appreciate HyperLogLog, it helps to understand the mathematical intuition behind why counting leading zeros works so well. When we hash an item to a seemingly random bit pattern and look at the number of leading zeros, we're essentially asking, how rare is this pattern? A pattern with more leading zeros is rarer. Here's the key insight. If we've seen n distinct items, the probability that none of them hash to a pattern with k leading zeros is 1 minus 1 over 2 to the power of k, all raised to the power of n. As n gets larger, this probability approaches 0 for larger values of k. For example, with just 10 unique items, the probability of seeing at least one hash with 4 or more leading zeros is about 48%. With 100 unique items, the probability of seeing at least one hash with 7 or more leading zeros is about 54%. With 1,000 unique items, we expect to see at least one hash with 10 leading zeros. With 1 million unique items, we expect to see at least one hash with 20 leading zeros. This is why the maximum number of leading zeros observed gives us a logarithmic estimate of the cardinality. And by using multiple buckets, we reduce the variance in this estimate. It's worth noting that this relationship between extreme values and set size appears in many contexts in nature and statistics. For instance, if you measure the height of the tallest person in a group, that height tends to increase logarithmically with the group size, not linearly. HyperLogLog cleverly exploits this statistical property for computational advantage. Engineers have long understood that perfect precision is rarely necessary or even desirable. An engineer designing a bridge doesn't calculate stresses to 20 decimal places, not just because it would be impractical, but because material variations, weather conditions, and other real-world factors make such precision meaningless. Similarly, in data analytics, context determines necessary precision. If you're counting website visitors to analyze trends, does it really matter if the actual count was 10,243,587 instead of the estimated 10,450,000? Probably not. But the resources saved through approximation can be allocated to other valuable tasks. What makes HyperLogLog and similar probabilistic algorithms so beautiful is that they don't require faster computers or more memory. They're conceptual breakthroughs that let us solve seemingly impossible problems through mathematical insight. In the realm of big data, as in many aspects of life, sometimes the wisest approach isn't to demand perfect precision, but to know exactly how much uncertainty we can afford.